Hello, this is reading quiz number 8, the last reading quiz in our set of reading quizzes for our unit on limits and continuity and the basics of derivatives. Today's topic is the topic of differentiability, which sounds like a really complex word, but we'll break it down and try to understand it in the context of calculus. So, some definitions first. A function that has a derivative at a point is said to be differentiable at that point. There are a variety of ways in which a function might not be differentiable. We've seen a couple of situations where the function is differentiable. For example, polynomial. Polynomials don't generally have any problems. But we could have a variety of different problems that would cause our function to not be differentiable. Basically, a function is not differentiable if it does not have a single slope at a particular point. Two examples on this page here. We've got the corner on the left, and we've got a cusp on the right. A corner is a situation such as with y is equal to absolute value of x, where the function is not differentiable at x is equal to 0. And the reason is because the left side derivative does not match the right side derivative. In our case here, the left side derivative is the left side piece of the piecewise function y is equal to absolute value of x. That piece is negative x when x is less than or equal to 0. In that case, the slope of the absolute value function would be negative 1. The right side piece is the function y is equal to x when x is bigger than or equal to 0. In this case, our slope is equal to positive 1. So we've got a slope of negative 1 on the left side and a slope of positive 1 on the right side, and the left and the right side derivatives don't match. On the right, we've got a cusp. Our most common example of that is the function y is equal to x to the 2/3. This function is not differentiable at x is equal to 0 for the same reason the left and the right side derivatives don't match. What makes a cusp different from a corner, though, is the fact that the left side piece and the right side piece are both going to different infinities with their slopes. As you can see in this picture, the left side piece, which is the one in blue, has a slope that goes to negative infinity, and the right side piece, which is in red, has a slope which goes to positive infinity. Two more examples of slopes that are functions that are not differentiable. The vertical tangent, an example of that would be y is equal to x to the 1/3, and this function is not differentiable at x is equal to 0. In this case, the slope on either side of x is equal to 0 is approaching positive infinity. You can also have a situation where the slope approaches negative infinity. Both slopes, both the piece in the blue and the piece in the red, are approaching positive infinity, which makes it different from the cusp. Our last situation is a regular point of discontinuity. For example, y is equal to absolute value of x over x. That function is not differentiable at x is equal to 0 because the function is not continuous at x is equal to 0. So let's say that we have some sort of an equation, like f of x is equal to x minus 3 to the 2/7. We can see from the graph that this function is not differentiable, right? And the type of non-differentiability is a cusp at x is equal to 3. You can see that the blue piece has a slope that approaches negative infinity, the red piece has a slope that approaches positive infinity. And you can check that by graphing. Now, later on, we'll be able to show that the derivative of this function is 2/7 times x minus 3 to the negative 5/7, rewritten as 2 over 7 times x minus 3 to the 5/7. If you plug in a number to the left of 3 and a number to the right of 3, you'll see that the derivative approaches two different infinity values on either side of x is equal to 3. An important theorem, which we'll call informally the DC theorem, and it says that if a function is differentiable at x is equal to a, then that function is continuous at x is equal to a. Part of the thing that we'll do later on in class is we'll actually go through and prove this theorem, but you can accept it for now. Note that the DC theorem is not the official name of the theorem, it's just a mnemonic device. And also note that the converse is not true. A function can very well be continuous but not differentiable. Our simple graph of y is equal to absolute value of x is an example of that. This function is continuous at x is equal to 0. In other words, the function reaches its intended height. but the function is not differentiable at x is equal to 0. As we mentioned on the previous slide, there are two different slopes on either side of x is equal to 0. So, one thing that we will note, in case you're curious down the road, is since we define the absolute value of x as x when x is bigger than or equal to 0, and negative x when x is less than 0, our derivative of the absolute value function is a piecewise function itself. It is in fact 1 when x is bigger than 0, and negative 1 when x is less than 0. So keep that in mind for future lessons. Example 2 from the reading. Make the following function differentiable at x is equal to 1. We've got the function f of x, which is ax cubed when x is less than 2, and 5x plus b when x is bigger than or equal to 2. And I go ahead and give you the derivative, which is 3ax squared when x is less than 2, and 5 when x is bigger than or equal to 2. We'll be able to find those derivatives using the power rule soon enough. Our first step, in order to make this function differentiable, according to the previous theorem, we need the function also to be continuous. So, we need the function to be continuous, which means that we need to set the left and the right side pieces equal at x is equal to 2. And we also need to make the slopes equal at x is equal to 2. And that's a typo right there. It should read x equals 2. In order for the function to be continuous, you'll remember a previous lesson, we need the limit as x goes to 2 from the left of f of x to match the limit as x goes to 2 from the right of f of x. I want you also to note that these two functions these two pieces are continuous everywhere but 2 automatically, because we have a cubic when x is less than 2 and a linear function when x is bigger than or equal to 2. And both of those functions are, in fact, continuous on the real numbers. So the only part where we're confused and we'll want to make sure that we're continuous is that x is equal to 2. For the function to be differentiable, we need the limit as x goes to 2 from the left of f prime of x to match the limit as x goes to 2 from the right of f prime of x. So, taking a look at this, limit as x goes to 2 from the left of f of x is just 8a. We plug in 2 in for x. Limit as x goes to 2 from the right of f of x is 10 plus b. We plug in 2 to the bottom portion of our piecewise function. Doing the same with our derivatives, we need the slopes to match as well. We plug in x is equal to 2, and we get 12a for the left piece, and we get 5 for our right piece. And as you notice, we have a system of equations that we can then solve. We notice that 8a has to be equal to 10 plus b in order for the function to be continuous, and 12a has to equal to 5 for the function to be differentiable. This means, of course, that a is equal to 5 over 12. Plugging that into the first equation, we can then find out that b is equal to negative 20/3. And we can check this with our calculator by plugging in a and b. And I've got a graph to the right which shows that when we connect these two pieces at x is equal to 2, you can see that the function is connected properly, meaning it's continuous, and the slopes match because there are no sharp corners or breaks.